Now we're thinking about the energy that is carried by waves. We know that waves carry energy because any bit of mass that's in the path of a wave will start to oscillate when the wave passes by. And of course, as the mass is oscillating, it now has energy. While it's moving, it has kinetic energy, energy that it did not have before. It must have gotten that energy from somewhere. It got the energy because the wave did work on that mass. The wave carries energy, and then the wave gives energy to the mass in the path of the wave. And when we think in a little more detail about the energy carried by a wave, how the energy is carried by the wave, we'll be thinking in terms of a source that is sending out waves in every direction, say a siren sending out sound waves in every direction, or a light bulb sending out light waves in every direction. And we'll picture it like this. Just imagine what's going on in just one plane, and then our source is in that plane. And if you look at all the points that are at one particular distance from that source, at all points, that same distance from the source, all points will have waves in exactly the same state. That the way I've drawn it here, all points on this circle are points where the mass that's in the path of the wave, as it oscillates back and forth, is at its maximum displacement on the positive side, away from equilibrium. Maximum displacement on the positive side. And then go out a little farther at all points that are a larger distance away. All masses will be at the same point in their oscillations, maximum distance away from equilibrium on the negative side, as I've drawn for these three places, and then go a little farther still and look at all the points on that circle, all the masses at each point on that circle are at the same point in their oscillations. They're at maximum displacement away from equilibrium on the positive side. And these, remember, these are called wave fronts. The book describes these as wave fronts. Wavefront is just the set of all points where all the masses are in exactly the same state in their oscillations. The way I've drawn it here, every bit of mass on that circle is at maximum displacement away from equilibrium. And then the next circle shows the next distance away from the source, where all masses are at their maximum displacement away from equilibrium. And of course, remember, this wave is being emitted in every direction, so these circles are really just two-dimensional slices of a sphere. And every point on that sphere is a point where the oscillating mass is at its maximum distance away from equilibrium on the positive side. And this is a smaller sphere where every mass on the surface of that sphere is at its maximum distance away from equilibrium on the positive side. And then halfway between those two spheres, you could imagine another sphere, and on that one, every mass is at its maximum distance away from equilibrium on the negative side. And as time goes by, you would imagine each of these spheres expanding at the wave speed, and that's how we can picture a sound wave or a light wave emerging from some kind of a source. And of course, since these are all the points that are at the same oscillation state, and this is the next time all points are at exactly that same oscillation state. Going from here to here, you've passed through every other kind of displacement that a mass could have, so the distance between here and here is exactly one wavelength. Or the distance between here and here is exactly one wavelength. Two numbers that we use to characterize the energy in a wave. Energy, power, that's just the amount of energy that carried by a wave that passes through any particular point in any amount of time. Energy per time, joules per second. That power is the rate at which energy being carried on that wave passes by any point in the path of that wave. The units are joules for energy, seconds for time, but we usually don't say joules per second. Our synonym, our unit label synonym for joules per second is watts. A 60-watt light bulb, for example, carries energy away on the light waves that emerge from it, and those light waves are carrying away 60 joules of energy in every second. The important thing to notice here is that if we look at just one particular distance away from the source, there's a certain amount of power passing through the sphere that has that distance for its radius. Think of each of these spherical wave fronts as passing by a certain distance. There's energy carried on each of these spherical wave fronts, and then all that energy carried on that expanding spherical wave front passes through all the points that are some distance away from the source, and the rate at which energy passes through all those points that are at some particular distance from the source, that's the power. But here's the thing, on any particular wavefront carries a certain amount of energy. As that wavefront expands, when it gets farther away from the source, it's still carrying the same energy. Energy doesn't disappear. It's still carrying the same amount of energy. Energy is just spread out over a larger surface, but it's still carrying the same amount of energy. And these, all the points on this sphere are still moving at the same speed, the wave speed, at the speed of the wave. So the same amount of power, or the same amount of energy, passes through all the points this far away from the source, and the same amount of energy passed through all these points a little bit earlier, and that same amount of energy is passing through all these points at the same speed at which it passes through all these points. So the rate at which energy appears at all these points at one particular distance is the same as the energy per time at which energy passes through all points a greater distance away. For any particular distance away from the source, it's the same amount of power. We just add up all the energy per second passing through each point on this circle, and it's the same amount of energy per second passing through the bigger circle, because energy doesn't disappear as that circle expands. It's always carrying the same amount of energy. The other number that we use to characterize the energy carried by a wave is intensity, and that number does change with distance. Here's the rule for energy. It's just the power per area, the amount of power deposited in a certain amount of area, or watts for power divided by meters squared for area. You can think of it as the energy that is deposited in 1 second and deposited on an area of 1 square meter when the wave hits that area of 1 square meter. Now let's look at some of the implications of this. Imagine you've got a laser beam, a laser pointer, and it makes a spot on the wall. And, spot's actually going to be much smaller than that, but I magnify it so it's easier to see what's going on. And let's say the radius of that spot is just r meters, and the intensity of the light wave hitting that spot, let's say, is 10 watts per square meter. Now, imagine that we remember intensity is power divided by area. Now imagine that we send that light beam, that laser beam, through a lens that focuses the beam down into a smaller spot, a spot with just half the radius. Half the radius of the first case. Well, the radius is smaller, so the area is smaller, but it's the same light beam, so it's carrying the same amount of energy, and all that energy is traveling at the same speed as before, so the same amount of energy reaches that spot in the same amount of time. Power is the same in both cases for both spots. It's just now in the second case, that light is focused down into a smaller area, so greater intensity, and that would show up as a brighter light. Area that the light wave is landing on is, of course, a circular area, pi r squared. So we can think of the power here as just power divided by that circular area, pi r squared. Power is the same no matter what the size of the spot is, and of course pi is the same no matter what the size of the spot is. So what we have are constant factors divided by square of the radius of the spot. In other words, we have an inverse proportionality between intensity and square of the radius of the spot. Those two variables, intensity and radius squared, are inversely proportional to each other, so when one variable changes by some factor, the other variable changes by the inverse of that factor. You've heard that slogan many times, and if you're still having trouble with the concept of proportionalities, learn that slogan. Repeat it to yourself until it becomes the first thing you think of when you hear the words inverse proportionality. Once you get over that hump, it'll make a lot of other things much easier. So r squared is inversely proportional to the intensity, so r squared is changing by some factor. Intensity will change by the inverse of that factor. We know how r itself changes. R itself changes by a factor of 1/2. The new r is 1/2 of the old r. We need to know how r squared changes because that's the variable that has the proportionality relationship with intensity. Multiply this or square this whole equation, and you'll see how r squared changes. The square of the new r is square of the right-hand side, which is just 1/4 times square of the old r. The variable called r squared changes by a factor of 1/4. So intensity, being inversely proportional, changes by the inverse of this 4. The new intensity is 4 times the old intensity, so the new intensity is 40 watts per square meter, or to put it more qualitatively, the spot is 4 times brighter. Now let's look at another situation where intensity will change when some kind of a length or distance changes. Here's a source, and then here's, this is just a two-dimensional slice of some sphere. The sphere being all of the points that are the same distance from the source. We'll call that distance d1. And the intensity on that surface is just the power, number of joules per second, the number of watts emitted by the source, divided by the area of this sphere. Geometry tells us that the area of a sphere is 4 pi radius squared. In this case, the radius of the sphere just corresponds to the distance, how far away all these points on the sphere are from the source, which is at the center of the sphere. So I'll use distance instead of radius. They're referring to the same thing. But of course, power is the same, however close or however far you might be from the source. Power is the same regardless of what d is. 4 pi is a constant, so again we have an inverse proportionality. We have constant factors divided by d squared. So intensity is inversely proportional to the square of the distance away from the source. And that's true for any kind of a wave, light wave, sound wave, any kind of a wave. And here's just one example of that. Let's say keep this result here. Let's say you're at a concert in an outdoor stadium. The stage is set up near what would be the end zone if they were playing football in that stadium. And so 10 yards away from the end zone, so approximately, roughly, same as 10 meters, you measure a certain intensity. So here's the source, and then at all points, a distance d1, where d1 is just, let's say 10 meters. The intensity is 0.1 watts per square meter. For a sound wave, that's really, really loud, and the musicians will all be wearing earplugs if things are still that loud 10 meters away. Now, if you go, let's say, have midfield, so that now you're about 50 meters away from the source. Here's just one arc of the one little piece of the sphere, which represents all the points 50 meters away from the source. What's the intensity that you would measure there if you had a sound meter? We use the inverse proportionality between intensity and distance squared to figure that out. And we could do it like this. The distance increases by a factor of 5. So we need to know how distance squared changes. And because distance squared is the thing that is related to intensity, that'll tell us how intensity changes. Distance squared, we figure out how that changes just by taking the square of that equation. Square of the new distance is 25 times square of the old distance. Well, the variable called distance squared changed by a factor of 25. Since intensity is inversely proportional to that, intensity changes by the inverse factor. So intensity changes by a factor of 1 over 25. The new intensity is 1/25 of the old intensity. And when you do the numbers, that'll come out to about 4, well, it comes out to exactly 4 times 10 to the minus 3 watts per square meter. Still really loud, but not dangerously loud. Not as likely to damage your hearing, whereas an intensity like that certainly would. Okay, that's one thing that you'll notice if you look at a table of intensities in chapter 15. Sound waves, like a lot of other different kinds of waves, have a really, really huge range of different intensities. So they have a huge range of different intensities if we're measuring them in watts per square meter. So the next thing we'll think about in the next video is a different way, a more convenient way of measuring different intensities that doesn't involve such a ridiculously large scale of large range of values.